Okay, so let's go. Good morning again, everybody. Thank you, Lucio, for the invitation. Today I plan to give you a brief talk about the. Actually, I had thought about an introductory talk about the spectroscopy that we can do here at a synchrotron. But now I add a few slides at the end to show you some specific cases that may interest you guys. So everything starts when we realize that matter, it doesn't matter if you are talking about biological stuff or solid crystals or water. Everything is made of atoms, and atoms are made of electrons. And we are very lucky that X-rays interact very strongly with electrons. So that we can use X-rays to probe electrons. And that's the idea when we talk about spectroscopy. Here I remind you about the electromagnetic spectrum, which has wavelengths from meters, more than meters, to picometers, and everything is electromagnetic waves. So the idea is that if you have different wavelengths, different energies, the electromagnetic radiation can interact with different things of different sizes. And in the synchrotron, we have a very broad spectrum. Then we can have infrared radiation, visible light, ultraviolet, and X-rays. Now I'll concentrate on the X-rays, because the X-rays, as I mentioned before, interact with electrons. And if we remember the most simple electronic structure, which is in this case here, I think it is the electronic structure of an isolated iron atom. We see that we have electrons with different binding energies, ranging from a few electron volts, tens of electron volts, hundreds of electron volts, and thousands of electron volts. So we need a source, X-rays. If you have an X-ray source that can produce photons with this broad range of energies, we can use this to do spectroscopy. And in this sense, when we talk about spectroscopy, the spectroscopy takes advantage of this, that atoms and molecules absorb and emit light in characteristic wavelengths to study materials' electronic structure. That's the main idea that I want to show you. But how does it happen? The core is the radiation-matter interaction. So if we have a source, in this case I show you a synchrotron, then we can get photons, incident photons, getting a sample. And as a product of the radiation-matter interaction, we get emitted electrons, transmitted photons, emitted photons with same energy, with different energy. I mean, we can have photons elastic scattered or inelastic scattered, and we can use this to study the electronic structure, to get information about chemical composition, about atomic structure, about magnetism, about luminescence, and everything related to the material structure. And then we can have, depending on what product of the radiation-matter interaction we are interested in, we can have different spectroscopy techniques. And now I want to focus on the emitted photons to talk about a very interesting technique, which is very new. There are just 5 or 6 around the spectrometers to have this technique around the world. And we will have a very nice spectrometer here at the LNLS. So basically, we ignore the other products and we look just at the emitted photons. And to do that, we are building here at one of the Sirius beamlines this monster here, which is its weight is about 6 tons, and it measures about 6 meters. So it's a monster, which we call the BRICS, the Brazilian Resonant Inelastic X-ray Scattering Spectrometer, at the IP beamline, which is the beamline where I'm working. So focus, what is RICS? The RICS process, if we look at the electronic structure, it starts with a photo absorption. The photon, which has a momentum and an energy, incides and excites an electron from the core level, and it does a transition to an unoccupied state just above the Fermi energy. Then we have an intermediate state before the decay process. Well, after the photoabsorption, the atom must get back to the ground state. So the electron, another electron must fill the core hole. But in the RICS, we consider this intermediate state, which has a core hole. And this core hole has a very high electrostatic potential that shakes up the electronic structure of the atom. And this core hole, this potential, can interact and excite qualitative excitations of the material, such as magnons, phonons, and this kind of stuff. As I mentioned, the Higgs, if we can measure the energy, so if we can have the energy transfer between the photon and the system, and to do that, we need to measure the energy of the emitted photon to compare with the energy of the incident photon and see which is the energy loss after the Higgs process. And if we can measure the momentum transfer, then we can do very nice things that I want to show you in the next slides. Okay, but this is an example of the RICS energy loss spectrum, which I took from the Wikipedia. It's here you can see basically the kind of excitations that we can measure by Higgs at solid samples. So you see that we have some excitations about a few electron volts, which are local excitations of the electronic structure of the material, and that are related to, for instance, dB transitions, and then we can use this to get information about crystal field theory and this kind of stuff. And if we go to milli electron volts, we can see these qualitative excitations, such as phonons and magnons. Well, you know that qualitative excitations can be considered as quasi-particles, in the sense that they have momentum and then they propagate along the material. So just to remember about the concept of dispersion relation of propagating particles, you know that a classical particle has a dispersion relation, a parabolic dispersion relation. A photon propagating in a medium has this linear dispersion relation. An electron in metals, depending on the origin of the interactions, can present different dispersion relations. And the dispersion relation is the most fundamental information that we can have about the transport of the particle. And if you know the dispersion relation, we can infer about all the macroscopic properties of the material. So the question is how to measure transport properties of collective excitations, and the Higgs allow us to do that. So we can measure dynamics by Higgs. As I mentioned, the Higgs process involves energy transfer and also momentum transfer. So if we measure the energy of the excitation and the momentum, we can measure these dispersion relations of the quasi-particles, the qualitative excitations. And that is very nice, for instance, for studying quantum materials, strongly correlated electron systems that are where different interactions between these different electronic degrees of freedom that comes from orbital excitations or lattice excitations or spin excitations or charge excitations that are coupled most of times and are behind the superconductivity, the more exotic magnetic orders, the emergent properties of these materials. So Higgs can be a very important tool to study this kind of stuff, for instance. And the other case, which I think is more close to the laboratory in Santa Maria, is that we can measure dispersion relations of spin waves, magnons, which are very important for magnonics, for instance. So I show you this slide, which I took from this Nature Physics paper about 6 years back, which presents a kind of a revival of magnonics, because the magnonics has been studied for 5 or 6 decades, but now people are start to focusing on high frequency magnonics. Then the idea is that for the last decades, we could measure very well, as you do in Santa Maria, for instance, dipolar spin waves, that are in the gigahertz frequency range. And that's easy because we have equipment that we buy commercially to measure impedance methods, vector network analyzer, ferromagnetic resonance, FMR, Brillouin light scattering. This kind of techniques is very easy if you have money, etc., to have in the university lab. But if we consider the most simple model, which is the Heisenberg model, the Heisenberg Hamiltonian, we see that we don't have just the dipolar magnons. We have also the exchange magnons, which comes from the exchange interaction. And the exchange magnons have modes at very high frequencies, at very high energies. For instance, going up to tens and hundreds of milli-electron volts, which are in the terahertz range. And the terahertz range is very complicated to probe with commercial equipment. But they are very interesting, because if we can tailor terahertz magnons, we can get ultra-fast group velocities and nanometer wavelengths. So this is very interesting for magnonics, for instance. But the problem is that we have just a few experimental techniques that can probe that. And most of them are the inelastic techniques, the inelastic neutron scattering, and the spin polarized electron energy loss spectroscopy. But they are very hard, experimentally speaking, because in elastic neutron scattering, for instance, you must have bulk samples, very big samples. And for electron spectroscopy, you probe just the first layer on the surface. So Higgs, which is the most new technique in this group, has a tremendous potential to give a next step to these studies. I don't want to take more time, but just to give an example that even the yttrium iron garnet, which is the most well-known magnonic material, the full magnum spectrum of YEG is still not fully understood because it's not measured. So in this paper, they show that the theory prediction fails to describe this range of the spectrum, of the magnonic spectrum, which is very important in room temperature, for instance. In this other example, for the first time a few years back, they used the electron spectroscopy to compare with first principle calculations and is explain the microscopic nature of the magnonic, the terahertz magnons in simple, very simple metallic samples, because it was impossible to do that before. But it's a very surface sensitive, this technique they use. So it's very exciting that the new RICS spectrometers around the world, one of them will be ours here at Campinas, are now measuring magnetic samples and showing that RICS can measure the terahertz spin waves in these kind of samples that before was very hard to do. So this paper is from the beginning of this year. This year is a Nature Materials. They measure the dispersion relation of magnons in very simple iron thin films to show effects of confinement in thin films. That's just to show you that so RICS is a complementary technique for these other more old inelastic spectroscopies, and we are very excited because it allows us to measure the dispersion relation of qualitative excitations, and this is critical to develop accurate microscopic models through the comparison between experiment and theoretical models, and therefore RICS can support the fundamental understanding of solid-state physics in quantum materials, strongly correlated electron systems, for instance, but also because RICS has been shown to be a very powerful spectroscopy technique to measure the dispersion relation of terahertz spin waves. This is a very important tool for terahertz magnonics to be developed in the next years. Okay, thank you.